The last part of today's tutorial is visualization and plotting. And in this process, we'll also answer the second question of our problem, which was where exactly or when exactly the terminal velocity happens. So if we look at our code again, we have a simulation running in the form of a for loop where we are getting a display of the data on the screen. But what if we want to plot it? So the command for that is called plot. And let's say I want to plot uh, value 0 on x-axis and 1 on y-axis with a red circle. So this command is going to plot uh, a graph where x-axis 0, y-axis 1 has a red circle. Okay, and I can put x label, y label, a title on this, which I will show as I implement this. So I'm going to close this for now and start the process here. So first we plot the initial value. So plot t0 versus v0 as a red circle. So these red circles will be our actual values. And then at this point I also want to give it a label, x label, and these are built-in commands. You should learn them how to use. X label is time in seconds, and you basically you can use single quotes to type in what the label, whatever you type here will become the label. And similarly, y label is velocity, and again it's good practice to put the units after that in parentheses and then close it with the single quote. And then of course the title of this lab 1 simulation result, for example. Okay, now I want this plot to add, this will be my plot, so I can quickly copy, and this is another way to do Control C copy, Control V paste, and you can see it has created this plot with 1 point. But I want all of the points to be added to this plot. Every time it runs through my for loop, I want those plots to be added. So I want to use a command called hold on, which means keep plotting on the same plot, and then at the end hold off. So stop plotting on top of it. And somewhere here what I want to do is add 2 more lines that will add this point VA and VN onto this plot. So that can be plot T versus V actual, which we are plotting as red circles, and also plot T versus V numerical, and let's plot these as blue axes. And as we do more labs, you will learn how to use this plot command. I would highly recommend going down here and typing help plot and see what the results are. Okay, but for now, let's say this basically should run the code, but before we run it for the whole, very fine, we will just run it for 1 second increment and see what the plot looks like. So it has plotted all those points, as you can see, and also those plots are displayed because of the display command that's still there. And you can see how a numerical solution, which is indicated by x's, slowly progresses based on its initial values, but the actual solution is different. And by the end, we have a certain amount of error, which we can reduce by reducing the increment. And now you can actually get a visual understanding of this. So let's reduce it to 1/100th of a second and rerun it, and you can see that the red circles and x's have gotten very close to each other, and by the time 10 seconds we are getting pretty accurate result. So how do we get the terminal velocity? Well, let's reduce it back to 1 second and increase the time to say 30 seconds. So now we will let this simulation run further into future and see where does this curve basically flattens, which means that the terminal velocity of a constant value has achieved. And it looks like it's going to be somewhere around 36, 37, but let's see what happens. So as we can see, it's actually not 36, it's probably 39-ish, and looks like around 20 seconds the terminal velocity, we have pretty much reached the terminal velocity. If you increase this any further, let's say 100 seconds, you will see that it will be pretty much flat line, so the velocity has become constant at that point. So this is how you can find the answer to the second question of this lab. So at this point, I would highly recommend you to try a couple of things. Go to the numerical and analytical codes. Make sure if you make a change in one, you make the corresponding change in the other one. And try to simulate by changing the mass or the coefficient of drag. And in your book, there's a problem, a numerical problem in your book. It's example 1.1. You can actually use the values from that problem to test if you're getting the same results as the ones in the problem. Also, something you can try is use, for example, the acceleration due to gravity for Moon, which I believe is 1.6, and see how would that compare with a free fall on Earth. Now, of course, you can imagine if there was air on Moon, but you can do it with and without air. So that pretty much concludes this tutorial.